Hello everyone, I am Preetham. Welcome to our TS session for week 10. So, mainly in this session, I'll be trying to cover some of the concepts which will be related to your charge sensing with the quantum point contacts. So, mainly the concepts related to quantum point contacts and single electron transistors. So, and the charging time associated, charge sensing, the time charging time associated with it. Mainly, we'll focus on this thing. So, whatever the problem were given, 1 second. Let me check once. Yeah. So what was the problem was given. So I'll try to. I made some sample questions and some concepts which will help you to solve the assignment problems. So I'll share my screen. So mainly we'll be discussing the two-dimensional electron gas that already we talked in a couple of times. So just a reminder, it is a semiconductor crystal which contains this heterostructure between two different semiconductors. So as you all see, I hope this is visible. So this is basically a compound semiconductor. Okay. So gallium arsenide, as you all know, it's a compound semiconductor, right? And basically it will be a junction of two superconductor as we are using here. So as you can see, this is two superconductors interface. One is gallium arsenide, another is aluminum gallium arsenide. So that's why it's a heterostructure, right? Of two different semiconductors. So you can grow it on gallium arsenide substrate, and then you grow actually in reality you grow quite a few different layers to accommodate strain and make a really high quality interface, right? So but just think about it as a substrate of gallium arsenide, then you grow this aluminum gallium arsenide on top of it, and so here on the side that I have for you, and a view top to bottom view of the band diagram that you can see, right? Observe material. So this is the band diagram for it. So along y-axis, so it's basically energy is plotted, and this is how the density is changing, right? So this is the band diagram of such material showing just the age of the conduction band. So the bottom of the conduction band plotted here, and the and this is the interface point. This one is the interface, as you can see, the interface point, it's right here, and the interface there, it's kink in the conduction band, which for a proper alignment of the other potentials, such as for proper amount of positively charged dopains. So as you can see, so here it's the ionized dopains we have used. Yeah. That donate their electrons to donate their electrons, the negatively charged electron that fall into the quantum well, and for the appropriate position of Fermi level, right? So we can just have just a single sub band occupied in this interface potential trapped, right? And this is the top view, basically on a three-dimensional crystal. Okay, this one. So This kink, this triangular well corresponds to a two-dimensional free electron gas, but constrained in one dimension, right? But in two dimensions, it's free. Here I show by this sheet, by this blue color sheet that you can see here. So in a typical structure, this would be buried about 100 nanometers below the surface crystal. So this will become important in this session. Actually, that is not on the interface in this case, but it's buried underneath the surface. Here are some typical numbers for one of these two-dimensional electron gas. Is now the first one is a density. This density is at low temperature, and so typically semiconductor would freeze out at this low temperature because all the excitations across the band gap will become impossible. But in this case there is this finite density which is quite sizable, also persisting down to low temperature, where a lot of quantum effects are observed, and this is because of the dopants, right, that are put here. So this extra dopants donate electrons that jump in and fall into the two DAC. So even at zero temperature, they are not frozen out there. There is an excess density, but this is relatively low density from point of view of uh, let's say of a metal, for example. So in metal, each atom donates an electron, and here maybe one atom per billion donates an electron, so the density is quite a bit reduced, right? And you can see that from the following energy scales here. So for example, Fermi energy is tens of millions volt here, and this can be just calculated from the two-dimensional physics that we discussed last time. So how many states are filled, and all the states inside the Fermi area are filled, and this will give you the Fermi energy, which is just a fraction of the Fermi energy which you can have in a metal. And that also means that these particles have a long Fermi wavelength. So you can calculate the Fermi wavelength by taking something like which some I mean some h bar divided by Fermi velocity, right? That is lambda. That's the Fermi wavelength. It's tens of, basically tens of nanometer. You can think. So just tens of nanometer. Okay. So let me write in a better way. It's the red one. So you can think of it as the size of the wave function of an electron, and that scale on which a single single electron wave properties should manifest tens of nanometers, means thousands of lattice sites. Thousands of lattice sites also is one electron, right? And then 5,000 and dimension tells you what's the doping corresponding to the number of total atoms. Okay, so then what is also important is that these structures are very ballistic in nature. So ballistic regime means that there is a very long mean free path, right? And this is you cannot really carefully engineering the semiconductors to be example by removing these dopants and not doping the kink itself by putting them a few nanometers away helps a lot. And for very high mobility structures, you can have this mean free path, right? Structure, and you can have mean free path of tens of microns, which is there's millions of lattice sites, you fly without scattering. And this is this is important going to be because for yeah, another thing I'm going to introduce today session is the gates. And these are the metals placed on top of the crystal. So that you can see, right? These are called the gates. Using this, we are going to apply some potential, right, to the system, either plus or minus, whatever. Let me check once. One second. So it's the gate, as I mentioned. It's placed on top of the crystal now. So to dimension electron gases 100 nanometers below, and these are metallic structure which can be nanofabricated to also be nanoscale dimension. For example, this gap, this gap, what you were saying, this one that you can see here, this gap is which is in the nanoscale and can be tuned to tuned down to 200 nanometer, as you can see. Such a tiny length scale, right? So, or something like this in this case, right? When there are two gates with a gap, this is called the split gate configuration. As I already mentioned here, this is called split gate. Okay. But I imagine just having a single gate going all the way across this two leg. This is what you can do with a gate. So you have a conductor which is a two-dimensional sheet, 100 nanometers below. Now I imagine you apply a negative voltage to this golden, which is also often made of gold. So that's why the color golden red gate. So will repel electron from the underneath, right? And you can think of it as a capacitor. um, you induce a negative charge on the gate that you will induce a positive charge on the to the deck, but to deck electron. As for the electrons, so full of negative charges, it's like removing electrons from the two deck. So adding positive charges like removing electrons from the two deck, right? And if you have a gate going all the way across for very negative potential on that gate, you can separate the two legs, right, into two parts in front of the gate and behind the gate, and those two regions will be unconnected because in between there will be a region of depleted of electrons. Think of a p-n junction diode, right? Remember, there is a depletion region in between. So there, this is what you can get with a gate, right? In the two two day. So this is also how you can make a field effect transistor out of two deck, right? So one single gate that cuts all the way across. Of course, you need to connect the front region of the two deck and the back region of the two deck, some charge reservoir. So charge can come and go. Otherwise, the charge will have nowhere to go and will not be removed from the underneath the gate. But this is how you can build devices with gates. And we have already seen this in the semiconductor devices a little bit. So now I'll move to the quantum point contacts. But now for the split gate device, I'm gonna apply a negative voltage to this gate, and I'm going to deplete the region underneath the gate of electrons, like I described already, and that will produce this region basically. Okay, produce this imprints of the split gate. in the two-dimensional electron gas inside this red lines, there will be no electron. There will be this region, no electron. Okay. So I'll write no electrons. Okay. But the constriction is so small that it is on of the order of the wavelengths. It's tens of nanometer, as I already mentioned. So 1 to 3 wavelengths of an electron, right? And this structure is then called the quantum point contact. This kind of structure is called quantum point contact. Okay. We apply the negative gate voltages through the metallic gates. So this is our first topic, right? And this is very important, and this wonderful example of one dimensional system. And this is great because this one dimensional system we can fully control by electrostatic, like just we can in principle change its width, although it's strange to talk about width of one dimensional system, but we can, I'll explain to you in what sense we can change the width. We can also in the in principle change the length, right? So it's a fully controlled system based on 2 deck. Now I'll move to the next slide. All right. So, but in essence, it's a constriction between inside a conductor and it's, and let's talk about what transfer of the charge across a constriction can look like from the most basic consideration. Okay. So if we want to transfer charge through a constriction, here it's another example of point contact, which is not necessarily quantum, but this was called Serpine. Serpine after a physicist who studied it. Okay, that is why it's Serpine point. It's called Serpine point contacts. And the key property of Serpine point contact is that it's very ballistic, meaning that there is a ballistic region where there is a very little amount of scattering. Okay, this is the ballistic region till this point. Very little scattering is there for the electron, so they can easily fly through, like in our 2 deck for 10 microns electrons fly without scattering. And then to pass a current through the constriction, we better connect this constriction into an electrical circuit, which will we can understand as having some contacts to the deck, right, to the two-dimensional electron gas, some contacts, and hook it up to the battery. And this would basically would look like this will have a region next to the left contact to the first contact, where electrons will be equilibrated to some chemical potential, right? That's mu1. So this chemical potential will be uh, this is mu1, the first one, okay, and will be whatever their Fermi energy, right, is there. It's EF. Fermi energy is there, is a plus E times V for one electron, E times V1. For example, so if the voltage difference is V, then this will be the chemical potential mu1, and then on the other side it will be sorry, other side it will be EF plus 0, right? Because one side we are applying with V. So I think I had flipped because the diagram shows voltage going in the other direction, but you get the point, so that the electrons will have the different Fermi levels raised, right? By the voltage, by the electric potential that we have applied here in this circuit. So now this electrons bounce around from the contact, and then they approach the constriction, which is in the middle of a very ballistic region. And then one of this electrons with the chemical potential mu1 just fly through the constriction as billiard balls, which may reflect, but does not change its energy, as that's the definition of the ballistic, right? So does not change its energy, even though its bounces of this also bounces elastically. So it does not change the energy, therefore it will only change the direction, right? So therefore you can see the red arrow here, it arrives to the other side of the constriction with the red arrow. This, sorry, to the other side of the constriction with the same potential. New one, it did not lose its energy, arrives, right? With that potential, it will then dissipate and lose its potential, its energy in this on its way to contact 2, but it crosses through the constriction without losing energy. So that's one of the key concepts for this thing, and that's why ballistic is important. There are also other trajectories which do not lead across the constriction, but can scatter you back, and that's the role of the constriction. So not all the electrons that fly from the direction of contact, one will make it across the constriction. Some will be reflected, and the fraction of those is given by the width of the constriction relative to the sample size, and so on. So the width of the constriction plays an important role here, okay? So and then there are also electrons with marked with blue arrows, which will go from right to left. This one you can see, right? Now these electrons have a lower energy, they have a lower chemical potential in my notation anyways. So but they still have, they have a random velocities as they leave the contact area, and some of them will fly across the constriction in the opposite direction while having a potential mu2. And now those electrons will subtract from the current because they are going in the opposite direction. So there are processes where you go across this way, across the other way, and you can also backscatter. And if we want to calculate the current, we need to count all the processes. In that's how I mean that's how transport calculations work, right? And we already have done some of these calculations. For example, we have done for the Drude model, right? But this is now short of looking at the atom of transport, one single constriction, and how electrons basically go across it. So in this sense, it's and so I'll now show you how you can build up transfer from any conductor based on this idea of splitting it into essentially a small constriction. Okay, so now the less the chemical potential difference, eventually electrons do lose their energy, although not in the ballistic region but outside. And so the energy difference is then given by EV, right? And conductance is given by current divided by the this voltage, right? So that we the voltage that is applied here. So the question is of course, how to calculate the current, right? This one. Well, in two-dimensional electron gas at low temperature, let's not calculate it first, but let's see what people have measured. This was actually measured in Delft in Holland on November 30th, 1987. I got this. This is a very famous experiment. So from their experiment, we have basically have we got this two plots. So these are very old data. From that group, this data were provided, so you can have a look on it. This is very famous experiment. Actually, I think this is not a proper slide. This this transparency with this machine scanned into a PowerPoint, but I still love to show because this is another, yeah. This cursor tells a lot. So it shows the resistance, which is then okay, the voltage is divided by the current or conductance for one of these constrictions made in a two-dimensional electron gas, just like I explained it to you. And now what's on the x-axis is the gate voltage. So it's in a experiment. They have just applied the same voltage on the two gates on the split gate, and they started with a more positive voltage. Okay, then they have made it more and more negative and the resistance increases, right? So let's first understand the overall increase. That is the relatively easy to understand, right? This one, as you can make the gate voltage more and more negative, you are closing to the constriction. So because you have this gates, and this is your to dig, and the electric field is not only goes straight down, it's also spreads and spreads like this. That's what I have drawn here. From the tips of the gates, and as you make more and more negative, you shrink the constriction, and as you shrink it more and more, electrons bounce back. The fraction of those that go across those trajectories shrinks, and so current basically eventually drops, and for the same potential difference, for the same voltage, you get a higher resistance. So that's the overall envelope here. And there is a formula for the German formula, which includes this one over with a factor with is the width of the constriction, and this is what we are observing here at first glance. It's 1 over width, but then there also, of course, this wiggles, that then at lower gate voltage. This is how it changes. This is Sorin's formula, yeah. So it's the more and more negative gate voltage, it becomes distinct steps, as you can see here. So there's a step like thing in the resistance, and then the steps also becomes equidistant if we invert the vertical scale and the plot now conductance. And this, and you have already seen such steps in quantum Hall regime, right? And they were quantized in the units of square over h. In this case, actually, it's a unit of 2 square over h. So he marked here, yeah, this one, 2 square over h. And they were able to observe quite a few of these steps. So let's discuss these steps in more detail. So now, yeah, let's move on to the next slide. So like I told you, we already seen something like this in the integer quantum Hall effect, and what I told you very briefly. So, and at the end of this session, that this was a steps comes from the fact that when you have a specimen at 2 deck in a large magnetic field, this, so you have this skipping, basically this orbit trajectories going on the along the edges of the system. This is the edge of the system, right? And the and in the quantum limit, they just become wave functions that are bound to the edges and form with a kind of one-dimensional channels. And then if you have several Landau levels occupied, that's like having several of running across along each edge of the for the proper, like this, proper choice of voltage and magnetic field. And I told you each one of them contributes square over h, right, this factor to the conductance. So now let's derive. So this is something that is in the common between the integer quantum Hall regime and this point contact regime, right? This seems to be the same observation. So will be good to understand where this comes from. So this is this part. Just carefully look in this. So all right. So we are in the ballistic regime, and moreover, we are in the quantum regime. We are at low temperature, and the constriction is of the size of the wavelength. So in the ballistic regime, like I already highlighted it to you, so I'm now not going to derive it. But basically, conductance is can be derived to be the proportional of the prefactor, which combines this fundamental constants and this factor. Okay. 2W by lambda f. and this is which contains the width of the constriction, right? This W, width of the constriction, and the Fermi wavelength, right? So that you can see in this ballistic, but still classical regime. You can have any conductance you want. As you continuously change the width of the constriction, conductance will increase, the resistance will decrease. Now we know that what to expect in the quantum limit of this situation. So when the width is of the order of the Fermi wavelength, right? So the wavelengths of electrons, then we know that it's equivalent to some kind of a particle in a box problem, right? So what is the box here? It's a box of with W that is mentioned direct, because we are in a two direct DAC. So we already constrain ourselves into two directions, in the Z directions, and so in the X, yeah, which represents the transverse. So X and Z, okay. So we can still have one direction unconstrained, which is along through the constriction. So this is a particle in a box problem where energy levels that are quantized and are in the exit box. Or if we just start with a 2D case, forget about Z, then it's a box in the X direction, and that's going to give us some quantized energy. 1, 2, 3, yeah. And this statement is that if you take this thing, if you take this formula and fit it here, when then when the width is exactly equal to certain values, right? So when this ratio W divided by lambda f is integer or half integer, right, of the conductance, exactly. So that's the factor, exactly the step values, right? I'm just going to say the W here is equal to lambda f, and this is exactly the case. Then the conductance will be uh, yeah, exactly quantized. Now it's still you can figure it out what the energy should be for this particle in a box problem. For a certain W, you are gonna get a certain energy, and you can say, well, we're gonna get a certain energy, and you can say, well, if one mode is exactly one mode is occupied, then you will have this conductance, right? So based on this formula, so this leaves a lot of there some gaps in this kind of argument. What if conductance is in between? What I if I increase W to be not to the integer of the wavelength with something else, but this will not make sense. So actually this we can get the quantized value for the exact ratios of this, but we cannot eliminate all other values. So we cannot produce shapes as a result. Just focus on this part. So you can stop me anywhere if you don't understand anything. Let me check once. So we cannot produce, yeah, and produce this kind of thing. So let's do that. Our first thing, we are going to make some realistic assumption here, and one is okay nomenclature. First, there is a left reserve and right reservoir. What is this one? Two reservoirs are there. Okay, reservoir one and reservoir two along the constrictions. So an excess transfers and apply some source to drain voltage. Source drain voltage, and we are going to measure the current that is going through, and we are going to calculate this current. And our first thing that we can safely assume is that the confining potential in this x direction is not a sharp function. It's not a really particle in a square box with infinite walls, sharp walls. It is some kind of a sharp confinement which we can approximate it as a parabolic confinement. So that you can see. We can consider this kind of thing. So that's because again you have this split gate and this to dig underneath and the electric field lines spread from the ends of the gate in this direction and gently gradually deplete. So the wave function is confined like this. So this is shown in red on the transparency, and then in blue I shown one of the eigenstates. This is the eigenstates. Sorry, this is the wave function. Sorry, this is a potential barrier. It's a parabolic. Need to decrease the width. Yeah, this is Vx. Okay, this is one of the eigenstate. This blue line. So if we say that, so the wave functions is confined like this, and so this is shown red on the transparency, and then blue is shown on the one of the eigenstates. So if we say it's a parabola, then we know exactly what the spectrum is going to be, right? It will be equidistant level, and the spectrum will be of that of a harmonic oscillator because that's particle in parabolic potential. So in this, so reasonable, right, and safe assumption. This is what we can do from here. The spectrum of one dimensional subbands in this wire and is that of a harmonic oscillator. So there will be some kind of wave functions. The first subband will look like this. This is the first, and this is the second, and this is the third one. Third subband will look like, okay, and so on. So that's in the transverse direction. What about in the longitudinal direction? What will be the dispersion relation, right? So in the x direction, we have this confinement, which is a parabola. So we have these solutions of the harmonic oscillator. What is going to look like in this direction? Uh, it's ballistic, yeah. Well, from the quantum mechanical point of view, so there is no confinement in this direction. Uh, P particles. So if I if I plot this, basically E naught E1 like this, E2 this levels. Okay. So and this axis will be ky. Okay. And this is obviously energy, which is it's going to be this along this direction. So this will be bunch of parabolas. Yeah, you can have certain energy in the x directions, which will be like an energy offset. You can in the zero mode in the x direction. You can be in the E1 mode, E2 mode, whatever. But then, why you are gonna have this kind of dispersion relation? So last lecture we and last session we mentioned this replay and one second. Mentioned this and we call this subbands, right? And this is because it looked like a band, but they're subbands because they live in the band structure of a semiconductor somewhere. They uh, arise due to some confinement imposed on the electrons as waves, wave packets in the already inside the main structure. Okay, so this is gonna be our description for this kind of. I can find a constraint, a constriction. Yeah, this will be several subbands. Each subband is one dimensional subband, so meaning corresponds to the free propagation in the y direction and the confinement in the x and also in the z direction, right? So here we go. So here is a spectrum drawn on a transparency, and now we are going to ask ourselves what's the current going to be the like if we apply a chemical potential difference across this constrictions, right? This. So this is where the fact that it's ballistic comes to play. And the way you can see it is that for all of the momentum in the positive direction, so here's ky is u for all the momenta. So in the positive directions, electron are going to have chemical potential mu1, and 2 shall mu. This is because ballistic, they have nowhere to keep their energy. So they start from the reservoir number 2 with the positive momentum, and they just go until they cross the constriction with that momentum. They don't change their momentum. Sorry, they don't change their energy. Momentum can be changed. So there are chemical potential, right? For the ones with a negative ky, likewise, the chemical potential is going to be mu1, and for for the chosen setting of these potentials, they cut across two of this one-dimensional subbands. So that means some of the electrons here, if you carefully see, this two, this transverse wave function is occupied. Some of the electrons in this transverse wave functions are occupied. Okay, so all the red states are empty and the green states are occupied. So it's mentioned. So these are the green states. And the chemical potential difference is even okay. So how do you calculate current? Well, I just start with the definition of current, that it's a number of electrons times their charge times their velocity, right? So just simply start with this formula, I equals to nev. Okay, so we certainly know all of these things. Let's put electron charge outside the bracket. That is some. Here is the sum over the transverse subbands. We were going to do the calculation separately in each subband, and then we are going to add it up. For example, from mu1 to mu2, we are doing the integration. For n equals to 1, so I think if we draw something, it will change. Actually, it's not fixing. This is the sum. Here is the sum over the transverse subband. We are going to do the calculation separately in each subband, and then we are going to add it up. So, for example, for n equals to 1, we are going to look at the bottom parabola and then and calculate the current for that. And then for n equals to 2, we are going to look at in the second parabola, and all the others will give us 0, all higher ones in this formula. Particularly case, right? And the formula is general. Okay, so then we need to know how many electrons are there. So we can just say that they're in or d, right? So, or we can use our knowledge of the density of states, which we already derived last time, right? Look at the green curve that I've shown here. That's the density of states for exactly this system for one dimensional. This one, okay. Look at this green curve. For one-dimensional constricted system, it is a peculiar density of states which we integrate. It's an energy plus tell us how many electrons we have. So then we can make this integral in so chemical potential from mu1 to mu2 as it's mentioned. You can see by structure of this integral, this is what just divided by the right. So it was integral of dm, but we made it in the integral over the energy. But yeah, with energy we'll do the integration. But what we have gained here is the density of states, right? We know which we have derived last time in its divergent function with fan of singularities, right? These are the van of singularities, the synonym. It's called VHS. This is VHS. These are van of singularities. Density of state where it diverges. With this thing, so and then it times the p in that's the velocity of the electron in its subband, and t is some factor of other unity which is transmission. So we can account for imperfect transmission because maybe some electrons are bouncing back, not making it across. That's where we account for those things. Transmission is finite. So when transmission is 1, it means that it's 100% of the electrons go through the transmission. Is that 0 means they're bouncing back, never make it from mu1 to mu2. uh, 1 second. And the Whittaker. Yeah, that's what those these are. And the in general, uh, we can allow them to be different for each of the one-dimensional modes for each of the subbands. So the one-dimensional density of states we derived last time, but may not in this form, but it happens to be this inverse of derivative of the dispersion relation. This is how you can get this band of singularity. You can see that is very clearly. So a function of electron and k is a parabola. E is a function of k, right? This one. It's a parabola. And now if we take a derivative of tk, so sorry, dEtk, that's going to go to 0 at the bottom of the parabola. Now the inverse of the derivative is going to diverge, right? That you can see. That's how you get the fan of singularity. That's another way of seeing at all right. And then we also know that velocity is actually the ddt of ddk, so first power not inverted.
And right, so that's just from energy being equals to mv square by 2. So velocity is some kind of proportion to the first power there, to the first derivative of energy inverted. So let's look at this integral now. We have the density of states time velocity, and one of them is proportional to the inverse derivative dk, and the other one proportional to the derivative itself. So that's very lucky, right? Because that's kind of cancel out. So density of states times the velocity. This one. This simply depends on the fundamental constants. Just a constant. Drops out all the dependence on k, on energy, all drops out. Is just a constant, right? So it's a beautiful result. And so this integral is just this gives us the current. This one ultimately is giving you the current. This is transmission coefficient. This mu1 to mu2. That's all time. It's a constant. So current is proportional to the difference in the chemical potential of the force. So more the difference of more the electrons can go across, and that's why current grows. But this is just this constant. Then times the sum of all the transmissions. So conductance is given by this one. Two square by which is the sum of all the transmissions for the sub one dimensional subbands, and if they are all yeah, so we have perfectly ballistic system, then the sum simply becomes the number of modes, just the then conduct and C, and the conductance is equals to C times 2 square over H. This one. Actually a result that you can apply to any conductance. This is this is known as Landau-Whittaker formalism. Okay, this is very important. You can think of about many conductors as having n number of modes. Okay, so large conductor, then you split it into regions, little regions is the size of the wavelength, and you can imagine that an, an arbitrary shaped large conductors contains a large very number of one-dimensional modes, and then conductance of that conductor will be n times the number of modes when it's perfect ballistic conductors. Now you can make the theory a little bit more complicated, allow the channels to scatter into each other, allow finite transmission, and then in the language of this kind of, as per the channel being to score the range of times the scattering transmission matrix, you can describe any process of electrons traveling through any kind of material. So this is a very useful formalism, and not just as a computational tool, which is also nice for those people who want to do the kind of calculation, but just at the conceptual level, for you to hold this picture in your head, right, so that you can think about the conductance in this quantum way. that there is, so let's say in a millimeter size of copper there will be a billions of one-dimensional modes of electrons, and they travel through this piece of copper.
Hello, am I audible? Hello,
Hello.
am I audible?
Am I audible?
Hello. Hello. So let's, yeah, there is some issue I think in between. Yeah, let's move to the next slide. I'll skip this one. Let's move to the slide number 11. So now I'll briefly discuss the charge quantization and the charging energy. So when the island is isolated, then the number of, then obviously we can put integer number of charges on it, and we cannot put 3.5, which has to be n times of the energy, n times of E, right? In terms of the charge of the electron. That's what it should be, where n is the integer. Okay, and that means that you can calculate the full energy of an island, which is E square times in divided by 2c. This is the energy. Okay, or if we call this EC, or the charging energy of the system, like just I introduced for you, then it's EC time n squared. So the energy related to the charge on an island grows quadratically with the number of charges. So what are some of the typical energies that we could encounter? So let's say 100 of nanometer. Okay. So this is, we have considered 100 of nanometers island, and right, I told you the wavelength in the dig is 50 to 50 nanometers. So this is of the order of wavelength in a 2 dig. Then we can have in a metal. So when each atom contributes an electron, 10 to 9 electrons in this volume of 100 nanometers, and then charging energy with this 10 power minus 8 electron volt is actually a fairly small, right? So because the capacitance is very large in this case. Okay, so if we don't have much electrons, then the charging energy can be so what is this One second. Yeah, sorry, delta I need to, yeah. So delta here is the energy. This is the kinetic energy that having this 10 to 9 electrons on an island gives you. Okay, so this is very small and we can neglect it. In fact, so there are some so few electrons on the island that their kinetic energy is very small, but the charging energy can be significant because it's of the scale of electric charge divided by the capacitance, which is proportional to the size of the island. So capacitance is proportional to the size of the island, right? C is proportional to L, and the charging energy for a 100 nanometer island can be about a millivolt, and that's much larger than what would be the Fermi energy of this small number of particles. Okay, sorry for bit mix up. And yeah, moving to the next slide. So I told you that there has to be an integer number of electrons, obviously, on an island. But I'm going to think to reduce something which is can be thought of as induced charge and second. Yeah, which can be thought of as an induced charge, and this comes from this kind of an electrical circuit. So in this circuit, you can see this part here. Our island, okay, this one, this focus on this part. So this part is our island. So this is a small volume of a 2 deck. For example, this part here is a gate, this part, which is connected to some battery, and other side of battery is hooked up to the 2 deck. So this is a reservoir which has a potential mu. Okay. So this is the other part of the 2 deck outside of the dot, and this is the tunneling junction, you can say. This one, this is the tunneling junction, you can call it. And so then we know exactly, it's a very simple electrostatic problem. We know exactly how to calculate it, that the total charge of the jump on junction is, you have to add a charge from this capacitor which is formed by the island with the gate, and you can model this tunnel barrier as another capacitor. So plus the charging used by that, so qg plus qr in the first equation. And now you also have capacitance to the reservoir cr and capacitance to the gate cg, and the total capacitance is sum of this two individual capacitance because they both go to the fixed potential outside. Now what does this mean if we introduce vi? So this potential, if we introduced, which is the potential on the island, this one, sorry, this one, okay, on the island, then the charge on the gate is equivalent to the potential difference between the island and the gate times the capacitance and the charge on the reservoir. So is Vi times, because it's Vi minus 0 is the potential of the reservoir in this calculation. and regrouping this just gives us this. This is the ultimate expression. Okay, just gives us c times vi, which is just the charge, right? The charge on the island, but then minus this cg times vg term, which can be thought of as an induced charge from the gate. And in principle, c times vi, this charge has to be quantized. It has to be equal to the number in, but this cg times vg, this can be anything because we can vary vg continuously. So this is the concept of induced charge from the external potential, right? Now quickly move through. Do need to discuss. So I'll just quickly discuss the some. No, only 20 minutes left for the discussion. So I'll simply quickly discuss the single electron transistor and transistor and some of the concepts, so that it will help you to solve some of the questions which was given based on the concepts on the single electron transistor. So give me a couple of minutes. I'll come back 1 second. So the working of single electron transistor is based on Coulomb block defect. So first let's see what is single electron transistor, and after that we'll try to understand what is Coulomb clock effect. And now a single electron transistor is similar to normal transistor, but some special cases electron transistor is one more important thing is the channel is replaced by a small dot that you can see. So this part of island, okay. So this is a small dot that is replacing here to do this thing. And yeah, the channel, this replacing the channel. So there is a source there, there is a drain here, this island, this small island, this one basically. uh, this dot is separated from the source and the drain. So this portions which separates this island or this dot from source and drain, they are separated with the help of insulator. Okay. Now electron which travels from the source, it has to tunnel the island in two steps. First, the electron will tunnel from the source to drain, as source to dot. Source to dot, and it's drain. Yeah, at the two junctions. Second is the junction. This is the island to drain. So this is some special features of a single electron transistor, which makes it different from a conventional MOSFET, right? So you can just quickly see all this. So basically, then Coulomb blockade. I have already discussed this thing and the Coulomb energy that you know. So in my earlier lectures, I have already explained you about this, and this is the quantized IV characteristics. So if you just quickly go through all the slides, I'm checking. I'm running out of time. So if you just go through this remaining slides carefully, so I think this will mostly, I have for today's session, I've mostly cleared all the, I've cleared all your like the doubts that we generally have while solving this kind of problem that were given in the assignments. So I hope this session will help you to do that. So I'll meet you next week then. So if you have any question, you can ask me. Also, you can ask me later. So I'm available through email, as I already mentioned in my last classes. So with this, I would like to end today's session. See you in the next week. Yeah, bye.